Hi everyone, I'm Johnny Giraldo. I am PhD student at La Rochelle Université in France. And today I'm going to talk about our work in graph convolutional neural networks for moving object segmentation in complex environments from unseen videos. So, what is the motivation of this work? As you know, deep learning methods require a lot of labeled information to avoid overfitting because in those kind of methods, we have pretty big models. And the idea in this work is to avoid these data-hungry methods by using the geometrical information that we can capture from the datasets that we are dealing with. And in this work, we are using graphs to capture this geometrical information from the datasets. The problem that we are facing here is moving object segmentation. And in this problem, we have videos. And in those videos, we have some objects that are static and some of them are moving. So at the end, the objective is to get the moving objects in those videos. And here we are using graph convolutional neural networks to solve the problem of moving object segmentation. Now, in the literature of moving object segmentation, we have unsupervised methods and also supervised methods. The problem with unsupervised methods is that they are very sensitive to changes in the lighting, if we have camera jitter, if we have dynamic backgrounds. These methods doesn't have any kind of feature learning. So these problems are very hard to address with these kind of methods. In the other hand, we have deep learning methods that are supervised methods, and so we can deal with these problems. The problem of convolutional neural networks, for example, is that they need a lot of label information to avoid overfitting. So what's left? One possible solution is to use semi-supervised learning methods in which we can learn both from label information and also from unlabeled information. And specifically here we are going to use graphs to accomplish this semi-supervised learning approach. So some very basic mathematical explanations. We need the definition of a graph. And a graph is basically a mathematical entity in which we have a set of nodes and a set of edges. In graphs, we have a very important matrix, the adjacency matrix. And this matrix tells us the structure of the graph. So for example, if we have a node, an edge between the node I and the node J in the graph, the entry I and J of this matrix A is going to be the weight of this edge. So that if we have an undirected graph, this adjacency matrix is symmetric. Another important definition is a graph signal. A graph signal is a function that goes from the set of nodes to the real values, so that we can represent a graph signal as a vector in Rn, where n is the number of nodes in the graph. If we are speaking about classification, this Y is going to become a matrix in M times the number of classes that we have. For example, in this case, we are dealing with a background or foreground. So this label matrix is going to be R n times 2 in that case of binary classification. Now, another important tool to understand the idea of this work is the sampling and reconstruction of graph signals. It's very important to understand what is a graph and what is a graph signal. So for example, here we have the graph structure, we have the nodes, and we know how those nodes are connected between each other. And on top of that, we have the graph signal that in this case are going to be the colors of those nodes. So for example, think of a graph of temperature. And for example, this node is New York, and this node here is Washington. So the colors are gonna be the temperature here in New York, this orange color, and this one more like skin color is gonna be the temperature in Washington. The problem of sampling is like getting some good nodes to sample. So for example, here we have the black nodes. In those black nodes, we don't know what is the graph signal in there. And at the end, we have reconstruction of graph signals, and the objective is to get the original graph signal as better as possible with the samples that we have and the structure of the graph. If we are speaking about classification, imagine that we have here some nodes and we have the labels of these nodes, and we don't know the labels of these black nodes. So we want to classify as better as possible the unlabeled nodes with the structure of the graph and with the labels that we have. So that's sampling and reconstruction of graph signals. And what is a graph convolutional neural network? So you know, convolutional neural networks have had a lot of success in problems in which we have very regular structures like images, audio, and so on. So what we want to do in graph convolutional neural networks is to extend the success of convolutional neural networks to graphs. So in graph convolutional neural networks, we have a similar structure. We have an artificial neural network. So for example, here we have an input graph, and we have some hidden units. And at the end, we are gonna try to classify something. This is a very famous propagation rule in the state of the art. Is this one here from Kip and Welling. And in this case, we have the adjacency matrix plus an identity, and we have the degree matrix of this perturbed adjacency matrix, and this HL is the input in that layer, so that in the first layer, HL is going to be the set of features of each node, and W is the weights that we are learning in each layer of the graph neural network. And sigma is an activation function, such as ReLU, for example. So that's the idea of graph convolutional neural networks. And now, what is the idea that we have to solve the problem of a graph moving object segmentation? So, in moving object segmentation, for example, we have frames, and in each frame we have some objects. So for example, in this frame, we have these two cars here are moving, so they are gonna be mapped to green nodes in this graph. And these cars behind these two are static objects, though, so they are gonna be mapped to blue nodes in the graph. And the black nodes are the nodes that we don't know the label in there. In a real scenario, we don't have this amount of label information, but instead we have very few samples, and we have a lot of unlabeled information. So at the end, the objective is to color this full graph as better as possible with the few samples that we have and with the structure of this data that we have, that we capture with the graph. Technically, we are mapping these objects to the graph with some segmentation algorithms. For example, with a mask RCNN, we can also have semantic segmentation, we can have superpixels, and even we can have block-wise segmentation. The representation of each node is accomplished with motion, texture, intensity, and background features. So at the end, a node is going to be a vector in a high-dimensional space. And the graph is constructed with a KNN algorithm. This problem of coloring this full graph is accomplished with the graph neural network. So this is the algorithm. Here we have some videos in the dataset. We segment some of the objects in those videos. We extract some features and we construct the graph. We also need some partial ground truth information to construct like the output of the GCN. And we need to take into account that we are gonna evaluate this in an unseen fashion. What does mean? What that doesn't mean? For example, if we want to segment this video for the training of a graph convolutional neural network, we are not gonna take any node belonging to that video. So that's the idea. This is the overview of our algorithm. And now I'm gonna show you some visual results. Here we have, this is our algorithm, GraphModNet. This is the previous semi-supervised learning algorithm that is also based in graphs. And here we have a deep learning method. I'm gonna show you also some videos. So here we have, for example, this is in the change detection 2014 dataset, and here we have the results in several challenges. For example, here we have shadows, and we can see the guy walking. Here we have also some results in challenging weather conditions. Here we have, this is very simple. This is in a baseline. We don't have like a great challenge in this kind of videos. In this one here, we have a camera jitter, like the camera is moving. Here we have some dynamic backgrounds, like the river is moving. And this is also pretty important because usually unsupervised method doesn't work in these scenarios of moving cameras. So here we have the results in moving cameras. The advantage of our method with respect to the previous semi-supervised learning method is that we are getting more positive, true positives. Now, those are some visual results and the videos. And here we have some more technical values. Here we have the previous semi-supervised method, and here we have our GraphMod algorithm. You can see that in almost all the challenges in the CDNet 2014 dataset, we have better performance. In these graphs, in these plots, here we have the training percentage with which we are training the graph convolutional neural network. So for example, this first point here is like 0.1% of training data. Here we have 2% of training data. Here we have 4%, 6, 8, until 10% of training data. So we can see that our method is better in baseline, dynamic backgrounds, camera jitter, bad weather, low frame rate, PTC, and also in intermittent object motion. So here we have some numerical results. Here we have the previous semi-supervised learning method and our GraphMod network. And here we have the result, in which this is in the UCSD dataset. This is a dataset in which we have moving cameras. And here we are training in CDNet 2014, and we are evaluating in this dataset. So we can see that, for example, the semi-supervised learning methods generalize better than this one here. That is a deep neural network that was trained in the CDNet 2014. And these are unsupervised methods. And as you can see, these methods hardly can do the job in moving cameras. So in conclusion, this work introduces concepts of graph convolutional neural networks in the problem of moving object segmentation. It's very important that with the geometrical information that we can capture from datasets, we can address problems of learning with minimal supervision. And I think that for future work, concepts of graph signal processing, such as active semi-supervised learning, could lead in new developments in the field of computer vision and end-to-end architectures for machine learning and computer vision. So thank you very much for your attention. Let me know if you have any question.